So in the last video we looked at the similarity within the right triangles when you have an altitude drawn from the right angle to the hypotenuse of the right triangle. We wrote out the statement of proportionality and we did find that for each one of those three pairs of similar right triangles we had a geometric mean. Well, there's theorems that correspond to that. So copy down these theorems and then we'll discuss them. So the first one has to do with the fact of the actual altitude itself, okay? So if we have this altitude drawn, remember altitude's a segment that's drawn from a vertex perpendicular to the opposite side, and if we're drawing the altitude from the right angle, it's going to intersect with the hypotenuse. Well, what this theorem says is that this altitude of CD is the geometric mean between the two hypotenuse segments that are created. So the point of intersection of the altitude intersects with the hypotenuse, then creating two segments. When added, make the original hypotenuse of AB. So this CD is the geometric mean between AD and DB. Now, we know that we could also just look at geometric mean as the square of the geometric mean is equal to the product of those two segments. So we don't actually have to set up like a proportion. We can say that the length of CD squared is going to equal BD times AD. And we could even take it a step further and say the length of CD is going to be the square root of the product of those two lengths. Okay? Now, the other geometric mean theorem has to do with the leg. Now, since there's two legs to a right triangle, there's two ways that we can actually look at this. So, the first one, let's look at CB. Let's call this X just to make things a little bit easier, okay? This leg of the right triangle. Now, if you think about it, this leg is two things. It's actually the hypotenuse of one of the smaller right triangles, see that? And it's also the leg of the largest right triangle. Well, this side here becomes the geometric mean, so we can say x squared equals between the small piece or the adjacent piece of the hypotenuse, so that would be dB, to the length of the entire hypotenuse itself. Okay, so from the adjacent piece of the hypotenuse and then the entire length of the hypotenuse. So then I call my other leg y, let's say. This y becomes the geometric mean between its adjacent hypotenuse segment, which would be AD, as well as the entire hypotenuse itself. Okay, so let's look at an example. It says write three different proportions based upon the geometric mean theorems. Okay, so let's go through this together, right? There's three of them. There's one that has to do with the altitude, and then the other one that has to do with the two legs. So let's first look at our altitude. Let's call this x, because I think it's easier when you have just a variable, right? So x, and we can actually say x squared, right? Because the geometric mean is when you take the cross products. This x is the geometric mean between the two hypotenuse segments. So x squared equals AD times DC. That's it. Okay, so let's look at one of the legs. So let's call AB y. So y squared, there's your geometric mean here, between the adjacent hypotenuse segment, which would just be AD, and the entire hypotenuse of the original right triangle, which would be AC. Okay, so let's call CBZ. There is our other leg of the right triangle. So z squared is going to equal what? You try to fill it in. Well, you're going to look at its adjacent piece of the hypotenuse, which is DC, times the entire hypotenuse itself of AC. And there's our three different, and now it says proportions, but remember that we could write like this. So if we want it in a proportion form, it will look like this. So our proportion, where our geometric mean is that repeated value, AD and AC here, and then our last proportion, if we had Z here and here, that would be DC and AC. Okay, so these are correct as well as these. All right, so let's throw some values in here. It says find the value of y in simplest radical form. So you want to evaluate, okay, are we looking at the altitude or are we looking at one of the legs of the right triangle? Here we're using one of the legs. So the leg is the geometric mean between the adjacent hypotenuse segment, which is given as 3, and the length of the entire hypotenuse itself, which is 9. So this is pretty easy. Y squared equals 27. So in simple radical form, we would get 3 root 3. Okay, let's look at another one. What type of geometric mean am I looking at? Well, you're given a leg of the right triangle, so we're using one of our leg theorems. The leg is the geometric mean between the adjacent piece of the hypotenuse, which is 4, and the entire hypotenuse itself of x. So actually this one's pretty easy. 36 equals 4x, so x equals 9. And last one here, let's look at what we have. We're not given either side or either leg of the right triangle. What we are given here is the length of the altitude. So the altitude is the geometric mean between the two hypotenuse segments. So that's just x times 4. Okay? That's the geometry. Now the algebra is what might get you. 4 root 3 squared. Well, remember, when you're squaring something, it means you're multiplying it by itself, right? So if we're going to multiply 4 root 3 times 4 root 3, 4 times 4 is 16. Root 3 times root 3 is 3, right? Equals 4x. So this is 48 equals 4x. So x equals 12. Okay?